covered the grid code requirement for controlling the voltage, frequency, load. Now we are going to talk about stability aspect of the grid. I had explained to you briefly for the generator, the load angle delta, which is angular separation between the EMF and the terminal voltage. Similarly, when the system is interconnected with various generating sources between the two machines, again the power flow is governed by the similar equation which we saw. Power flow equal to EA, EB. EA is the voltage at, say, the sending end. EB is the voltage at the remote end, divided by the impedance between the two terminals, X, and the angle between the two, sine delta. Here again, the maximum power flow occurs when delta is 90 degrees. Now, in terms of power and angle delta, you can see here for a given power, mechanical power, here the generator supplies the equivalent active power as an output and supplies to the grid. Now, what happens when there is a fault in the power system? When the fault occurs in the power system, say there is a fault here, at this point will collapse depending on the location of the fault and impede the fault point, and because the voltage goes down, the active power being fed by the generator, that active power will the reduced voltage, and accordingly the active power will collapse. But the mechanical power being the same on the turbine, there is again a difference between, in a steady state condition, as I said, mechanical power as a prime mover and the electrical output, they run in a steady state condition. When the electrical power,
सर आवाज कट रहा है, नहीं क्लियर नहीं आ रहा है.
हाँ सर, आवाज कट रही है आपकी, थोड़ी सी लगता है. अपना वीडियो बंद कर
you
दीजिए.
will see that there will be a short circuit causing a difference between mechanical input from the prime mover and electrical power, which is output. The machine will accelerate. So at this point, the machine will takes place. Now, accelerate. At some point of time, the fault will be cleared by the protector. When the fault is cleared by the voltage will.
नहीं है सर, आपका आवाज कट रहा है, कुछ समझ में नहीं आ रहा है.
The moment. अच्छा. But I can see the. Is everybody, because I am seeing stable connection and able to see the video as.
Sometime it's happened, sir. So I think either you can just restart your internet device.
सर इनकमिंग वीडियो ऑफ करने से भी हो सकता है।
Sir, I can usually I get a alert if the internet is unstable. So here my internet connection is showing okay.
Now it's okay, sir. I think you can continue, sir.
Is it okay? The connection now? Are you able to hear now?
Yes, sir.
Yes, sir.
Okay. So we are talking about the steady state condition followed by the fault taking place and then the fault getting cleared by the protection system, and in the process because of the power mismatch between the mechanical input and the electrical output, there is an acceleration followed by deceleration, and the new steady state condition will reach after this oscillation of acceleration deceleration. So when it is accelerating, the delta angle will increase, and the fault gets clear, it will start decelerating, then delta angle will start decreasing. This instability, this is a transient instability, and this instability will become steady after a few oscillations. Now, if the oscillations continue in a without damping, then machine will become unstable, because then it is the instability will continue to increase and oscillations will continue, and we experience the phenomena of power swing, and the severe power swing can result into pole slip of the generator. The modern excitation system, we talked about the response parameters, and one is the field forcing, which is the ceiling excitation level. Second is the response ratio, and in terms of speed, there is a rise time which we saw. This fast excitation system basically helps in maintaining the voltage at the terminal of the generator. So if there is a power system fault in the grid, the field forcing phenomena, because of the fast acting excitation, as well as the depending on the ceiling excitation capability, there will be field forcing phenomena which will try to maintain the terminal voltage constant as much as possible. The collapse of active power will be reduced, and the difference between the prime mover for the generator output will get reduced. Because of this, delta P is kept minimum, the instability will be better. That means the machine will remain stable and remain synchronism without getting out of step. So this is which is desirable in the excitations. Oscillations, and these oscillations will continue for a in an undamped manner for a long time, unless there is a corrective action by some generators. This corrective action in the generators by way of providing the counter excitation in the AVR is done by the power system stabilizers. So it is also mandated by the technical standard that machines, thermal power stations of 250 megawatt and above, hydro power stations of 100 megawatt and above, they should have power system stabilizers. What these power system stabilizers do, if there are inter-machines oscillations, in inter-area oscillations, which are typically oscillations of very low frequency. It could be 0.1 hertz or to say 1 hertz. So very low frequency oscillations, and you will see MW oscillating at a low frequency. These are the sort of oscillation which can be the action of power system stabilizer. So this is one of the countermeasures to keep the machine stable. The third action, which is possible those slides. Is basically the auto recloser. And this will be covering later during the protection month. But basically, the auto recloser is another measure which helps in stability. What
आवाज फिर डिस्टर्ब हो रही है सर.
सर आपकी आवाज
so
नहीं आ
that
रही है.
again the deficit. Okay. Yeah, is it audible now? I switch over to another network. Can you hear me now?
Yes sir, yes.
Yes, sir.
It is audible.
The slide is also can be seen.
Okay, yes, it is clear.
Sir, please repeat about auto recloser.
Yeah. So one of the action which helps in maintaining the transient stability is the auto recloser. And auto recloser basically for 400 kV by technical standard, it is mandated that single phase tripping and single phase reclosing is fast auto recloser is required. Basic idea again being the reduction in the line trip. Then between the two sending end and receiving end, the impedance, one line going out means the impedance will become higher. So the network to that extent will become weak and the delta P will rise when the fault takes place. With single phase tripping and single phase auto reclosing, this delta P is minimized, as well as the network change in impedance between sending end and receiving end, and that is also minimized. So this helps in again maintaining the transient stability, because again the angular separation between the sending end and receiving end will be then minimum. That's why single phase auto reclosing and is mandated for 400 kV system and above to maintain the transient stability. Now the parameters which affect response of a generator, again it depends on the size of the machine, depends on where is the location of the disturbance, and how much is the networks. If the network is strong, transmission network is strong, that means we call transmission network strong, means in our power equation X should be low. If X is low, the power transfer in this equation, if the X is low, suppose there are 4 lines in parallel, then the net impedance will become low. Net impedance between low means the power transfer capability will go up. So that's why low, if the line, suppose you have got 4 lines, and out of that 4 line, one corridor trips, that means both the lines go out. So the impedance will increase by 100%. Case, then the ability to transfer power will get reduced. So this is the transmission network, basically auto recloser will help in minimizing this sort of transient unstable condition. We talked about capability of the generator. We talked about the capability curve, and then we talked about the short circuit ratio, where we said higher the short circuit ratio, there is a better capability to withstand the short circuit, and machine can remain stable. In the same way, you must have heard that synchronizing power. When you close the machine with the grid, when the HV circuit breaker is closed, the angular separation between the machine at the instant of closing will decide the synchronizing power fed by the generator when breaker gets closed. So there are 3 parameters when you do auto synchronizing. Basically, it does auto synchronizing by 3 ways. One is they see the closing angle at the instant of closing, the terminal voltage and the grid voltage, how much is the deviation, and what is the frequency difference between the incoming frequency and the grid frequency.
Sir, here I have one practical question, sir.
Yeah.
Suppose we are synchronizing our machines to the grid.
Yes.
And during synchronizing, sir, we getting the PT voltage from the outside the delta side of start side of the transformer.
Yes.
So how when we take out the bus voltage towards the synchronous scope, so is there any change in the phase angle, sir? And if the angle is changed, then how it is compensated, sir, in synchronous scope?
So you are talking about a case where there is a synchronizing at 11 kV or lower voltage side, or on the EHV side?
Sir, delta in the power transformer, we are giving input through 11 kV as a delta, and we getting the outside of the transformer as a star. and the bus voltage during synchronize we require the bus voltage and generator voltage. So both are coming from the PT terminal. So both are a 110 voltage. That is no problem. But how the phase angle, there is no change in the phase angle as the voltage is transferred from delta to star. Is there any possibilities of phase angle change, or if change, then how it is compensated in the synchronous scope, sir?
Normally, the synchronizing voltage is taken from either side of the circuit breaker. That means if you have got a HT circuit breaker, then the synchronizing connection is taken between the generator transformer output and the bus PT. So both the voltages are taken from the EHV side only. In some configuration, as you say, you need to take the synchronizing voltage from one from LV side and one from HT side. In that case, there is a 30-degree phase shift which has to be corrected by auxiliary PTs. So you have to install auxiliary PTs and then take the corrected voltage in a single phase, even if you are taking single phase. But that phase correction is required through auxiliary PT. Nowadays, with the digital auto synchronizer, this phase correction can be done digitally by software also. If you have got a digital auto synchronizer. Is it clear? What I said?
Sir, yes, sir. Yes, sir.
So that phase correction will be necessary in case you are taking one from delta side and one on star side. Similarly, then there is the capability of sudden short circuit on the generator terminal. A generator should be capable of withstanding without injury 30-second three-phase short circuit at its terminal. This is the IEEE standard on which the most of the generators capability is based on. Now, the machine shall also be capable of withstanding without injury any other short circuit at its terminal for 30-second duration or less as per this IEEE standard, and generator circuit breaker needs to be selected accordingly. Now, any short circuit seen in the grid, we talked about the short circuit current which is being fed to the fault, and we have also seen the peak current is offset by DC offset, which is 2 times the steady state current, and the magnitude of this offset depends on X by R ratio. So the ability of the generator to withstand the external short circuits also depends on some of these parameters which we talked about. Though it is said that withstand capacity of 30 seconds, but this is a short time rating as far as the thermal heating of the winding is concerned. But electromechanically, if the generator terminal short circuit takes place, if there is a generator transformer in between the grid and the generator, then the generator transformer acts as a limiting the fault current for the short circuit on the grid side, and to that extent the impact of the generator is less, but the turbo generators, there is still a electromechanical force. That hydro generators which only withstand short circuits, and in terms of stability also they are good. Thermal generators which are high speed machines.
आवाज फिर से डिस्टर्ब हो रही है सर.
The serious condition, and if there Am I audible now?
पहले डिस्टर्ब आ रही थी, अभी ऑडिबल
Can you
है।
hear me?
यस, अभी ऑडिबल है।
So there is no
Yeah.
sound.
Can you hear me now? Am I audible?
Yes, sir. Yes, sir.
यस,
Yes, sir.
Okay. So we talk about synchronizing power when you do the synchronizing. That's why auto synchronizers is a better option than the manual synchronizing and manual synchronoscope. Similarly, the generator parameters like short circuit ratio also decides ability of the generator to withstand external short circuits. In case for some reason the manual auto synchronizer is not available, in that case the check synchronizing relay must be used along with synchroscope for manual synchronizing, because however skilled operation person is there, it is difficult to maintain the narrow angular difference and voltage and frequency difference by visual guidance from the synchroscope. So check synchronizing relay is recommended in case you resort to manual synchronizing. We talked about using generator as a voltage support to the transmission network. We had already discussed the three aspects of the AVR, where voltage set point of the AVR can be one mode of control. You can use the reactive power set point of the reactive power controller or power factor set point, whichever is available on the network in the AVR. And also you can use the tap changer of the generator transformer to control the reactive capability in case there is a on-load tap changer facility which is available. We talked about under-excited operation in the capability curve. And we also talked about the limitations on the under-excited side on two counts. One is related to the overheating of the end zone of the stator, and second is on the stability limit. In both these aspects, hydro generators are better performers to help the grid to absorb the reactive power when the grid voltage is high. This is something which has been recommended in the technical standard of the CA as well as in the grid code. But for reasons of these two limitations, where the people are apprehensive about overheating of the machine as well as hitting the stability limit, generally under-excited operation is not resorted to. But I suppose if there are enough incentives given for the voltage control ancillary services for reactive support, even the hydropower generators will start contributing to voltage absorption. In India, it was a common practice to switch off the lines during light load condition to control the over voltages. But switching of transmission line to control the voltage, you are actually jeopardizing the stability of the grid because you are weakening the transmission network. So reactive power absorption by generators wherever it is possible, I think it's a better solution to control the voltage, control the over voltage phenomena. And there are enough design aspects in modern generators which permit full use of generator in the under excited region as per the capability curve. So there should not be any fear of damage to the machine because of under excited operation. Are you aware of anyone can share the experience? Do you operate the machine in under excited region? Anyone from the participants can tell us? Is my question clear? Are you operating the machine in under excited region to when there is a over voltage in the grid?
Yes, sir.
We did by power ERLDC told us to because of high voltage grid voltage. So
Yeah.
So we did, sir.
Anyone else?
सर ऐसा जब ग्रिड वोल्टेज हाई हो करना पड़ता है under-excited.
Yes. Yeah. Now there is a regulatory provision also. So and maybe with the ancillary services for voltage support, this would be good source of revenue generation also. So these are the provisions in the technical standard also, where generators are encouraged to participate in voltage control. There is a difference between generators which are near to the load center and generators which are located far from load. Typically, the generating stations, hydro generating stations are always away from the load. And send reactive power all the way to load centers from the hydro generating stations over a long transmission line. But the stations which are relatively closer to load center, this reactive power support by supplying reactive power to the grid should be encouraged. Yeah, this is what the basically the conclusion that all the power plants are required to participate in voltage control. In order to achieve the voltage control, the excitation system of the generator operates within the reactive power set point or with the voltage set point or with the power factor set point. So these are the three modes of set points which are in control of the operator. The maximum amount of exported reactive power or absorbed reactive power at different levels of the output of the generator terminal is revealed by the capability chart of the generator. So this becomes your reference document. And as the technical standard mandates that though the guidance will be given by the load dispatch center, each power station has to operate within its capability curve. Reactive power absorbed by hydro generator as a rule are not restricted because there is no fear of any overheating, and stability wise also there is enough capability. So hydro generators are better performers in terms of voltage support when the grid voltage is high. So that is the basic conclusion. Now we'll look at some of the aspects related to system voltage and frequency on the transmission side. So far, we have been talking about the support provided by the generators. Now we'll see what are the aspects on the transmission network side. Fundamentally, if you see the transmission line, this is the sending end of the transmission line, this is the receiving end, and this is R and X of the transmission line. So just like a generator, here also we see this is the sending end voltage. Then there is a drop in resistance, drop in reactance, and this is the sending end voltage, and this is the receiving end voltages. The drop takes place in this, and the angular separation between the sending end and receiving end voltage is the angle delta between this, which will decide the power flow capability between the sending end and receiving end. So just like generator, for transmission line also, basic electrical principle of power transfer is same. The same thing is represented here. Now you can see from this voltage drop between sending end and receiving end is basically because of the reactive power flow and the reactance between the two ends. So we can say that the voltage drop in the transmission line is directly proportional to the reactive power flow. So there is an active power flow in the transmission line. There is a reactive power flow in the transmission line. So reactive power flow is primarily responsible for drop in the line voltage at the receiving end. During the light loaded condition, when the active power flow is less, and the reactive power flow on account of the load and the capacitive support provided by the transmission line capacitance basically becomes significant. In that case, there is a rise in voltage at the receiving end because of the capacitive power injection. So between the sending end and receiving end, if you, for example, inject the capacitive reactive power here, the voltage at the receiving end will see the rise. This is the same principle which is used for providing the reactive power compensation. So when we talk about STATCOMs or static power compensator, etc., usually they are provided at the receiving end of a transmission line, so that voltage at the receiving end can be maintained. In spite of the reactive power flow, the voltage at the receiving end can be maintained. This rise in voltage at the receiving end, because of the capacitive charging current which flows through the line, is called Ferranti effect. You must have heard many times the Ferranti effect, which causes over voltages of the line. That is the reason when there are high voltage condition, load dispatch will tell you to switch off the transmission line, so that capacitive reactive power which is getting injected into grid can be prevented. Typically, if you want to have an idea, a 400 kV line approximately generates 55 MVAR per 100 km per circuit. So 55 MVAR is per 100 km. So depending on the length of the line, you can see the substantial reactive support is given by the self capacitance of the line itself. Or that means for an average line length of 300 km, 165 MVAR will be injected into grid because of the capacitance of the line itself.
Sir, what is the formula? 400 kVA and 55 MVAR. How we calculate, sir?
This is based on the line configuration of the 400 kV line and the capacitance per kilometer, which is like you calculate inductance, you also calculate the capacitance of the line. So this is basically basic line parameters which decides this. Depending on the distance of your conductor spacing with respect to each other and with respect to ground and the tower. So the tower configuration decides. The tower configuration which is adopted in India, generally you can take this as a thumb rule, that 55 MVAR per 100 circuit kilometer.
ये सर आपने तो इसका एक ऑब्जेक्टिव दिया है ना?
ऑब्जेक्टिव मींस
आपने इसी के ऊपर एक ऑब्जेक्टिव दिया था, मैं देखा था.
कौन सा
ऑब्जेक्टिव क्वेश्चन?
हाँ क्वेश्चन, यस यस,
हाँ एक ऑब्जेक्टिव क्वेश्चन था इसी के ऊपर.
Yeah, it is based on one of this information only.
Okay.
But this is a well-known. Anybody who is working on the transmission line operation, they will usually have this.
Actually हमने इसका आंसर में गेस मारा.
Pardon?
तो ये मौसम के हिसाब से चेंज होगा ना, वेदर कंडीशन से?
वेदर कंडीशन से थोड़ा बहुत चेंज होता है, लेकिन इतना ज्यादा नहीं होता है. बेसिकली the stray capacitance plays the little bit role if the air is dry and air is moist, and also the condition of the ground depending on that. But that variation is not much. Maybe 55 ke jagah pe it could be 50 or it could be little more, but it is around that. So it's a thumb rule, so it's not very accurate, but just to give an idea that approximately 50 MVAR you can say per 100 km, just to give an idea. Of course, if the tower configuration is different, it will change again. Now, you can see here, for a given transmission line, there are two curves. One is the current profile and one is the voltage profile. You can see for an unloaded transmission line, depending on the distance in kilometer, it is 100 km, 200 km, 300 km. The receiving end voltage will rise as per this. So from see if the sending end is 1 per unit, the receiving end could be up to 1.08, so 8% rise in voltage. So this is how you will get a. This slide basically we had already discussed what happens when the line trippings occur. When you represent the grid by a two machine model. In two machine model, if there are number of lines which are connected, you can see the power transfer capability, you can see when all the lines in service, this will be the curve. This is the peak capacity which can be transferred without limiting the stability. If the one line goes out of service, the capability gets reduced to this value. If two lines go out of service, then this will be the further reduction in the capacity. You generally, as a general expression, system has become weak. Basically, system has become weak means the ability to transfer power without losing the stability becomes lower. So this is the power angle curve between two buses. This also, there is also a concept of line loadability and the voltage stability. Now, this line loadability, how much load a line can carry without dangerous voltage reduction, is again governed by what is called surge impedance loading. You all must have heard the surge impedance loading. Basically, the transmission lines as well as the cable, they generate and consume reactive power at the same time. They supply reactive power to the load, but at the same time, their inherent capacitance generates the reactive power. The reactive power generation is because the voltage of the line is usually constant and the line's reactive power consumption depends on the load. So at the heavy load condition, the transmission line consumes reactive power, decreasing the line voltage, and at the low load condition, it generates the reactive power, increasing the line voltages. That's why in the night time, you see the voltages go up because there is an excess of reactive power, leading reactive power. Now, surge impedance loading is when the reactive power produced by the line capacitance is equal to the reactive power consumed by the line inductance. So there is a L and C reactive power when they are matched. That is your surge impedance loading. At this point, what happens is the line provides exactly the amount of MVR needed to support its voltage. The point at which the inductive and capacitive effects can be compensated with each other. This is about 40% of the line's thermal capacity. Depending on the conductor, the thermal capacity can be much higher, but the surge impedance loading is lower because of this. Of course, it depends on the length of the line also. So line loaded above the surge impedance loading consumes reactive power, while line which is loaded below surge impedance loading supply reactive power. So this is basically the concept of surge impedance loading is important as far as the voltage stability of the transmission line is concerned. This slide gives only the calculation of MVR produced and MVR used. This is a famous St. Clair curve, which gives the line load limit as a in multiples of surge impedance loading and the length of the line. So you can just see for an average length of say 300 kilometer, you can see line capable of transferring the load approximately 1.4 times its surge impedance loading. As the line length becomes more and more, that capability keeps coming down. That's why when the line becomes very long, then you need to provide the shunt compensation or the series compensation depending on the situation. Typical values of surge impedance loading are given here. And this is called the PV curve. You can see here, this is the bus voltage. Here, sending end voltage, this side is the receiving end voltage, and this is the loading of the line. And you can see the curve, voltage profile of the line. And this voltage profile of the line, depending on the X, that is the net reactance. If there are number of parallel circuit, reactance values will be low. So the voltage drop due to reactive power flow will be low. But as the line trips and the number of circuits keep coming down, you can see the voltage collapse takes place at a much lesser loadability of the corridor. So with one circuit out, this will be the capability. You can see the below this is called the nose point of the curve. Below this, the voltage collapse phenomena will start. Why this happens? As the reactive power flow increases in the line, voltage will start getting reduced at the receiving end. At the receiving end, voltage becomes less. The loads which are conducted, mainly the motive loads, their active power will go down because voltage is less, and the reactive power will become high because the power factor is becoming poor. So reactive power is high, so more voltage will get dropped on the reactance. As we earlier also said, that voltage drop is proportional to the flow of reactive power and the reactance between the two ends. And further voltage will get reduced. So it's like a vicious circle. So voltage will come down, reactive power flow will increase, voltage will further drop, and ultimately it will lead to the nose point, which is like a knee point of a magnetic circuit. Below that, actually, the reactive power will be so high and the active power flow will become so low that voltage will start dramatically coming down. Now, this is called basically voltage instability. We earlier talked about angular instability, frequency instability, and this is voltage instability. For generators, we talk about angular instability. In the transmission, we talk about voltage instability. What happens in voltage instability? Something what had happened in the grid collapse of 2012. Basically, in that case also, there was a cascade tripping of the line. One after another, the line had tripped. Progressively, the load on the line had increased. The voltage at the receiving end reduced. The receiving end voltage had come down to almost, I think, 360 kV level. And at that point of time, the loading on the line, which was in normal condition 900 ampere, it had actually reached 1400 ampere because of very high reactive power flow, and the voltage collapse phenomena had occurred because the distance relays to operate in third zone, and then lines trip one after another, leading to collapse. So this is the voltage instability phenomena. We talked about stability and the impact on the fault clearance progressively as number of circuits. There is a cascade tripping. The system becomes weak and weak. When we talk about protection tomorrow, we'll also explain how this has impacted the philosophy of distance relay, power swing, blocking, and power swing tripping logic. Because when there is a power system instability, voltage instability, the high reactive power flow and overloading of the lines takes place. At that time, it becomes important that lines remain in service. What we have just now discussed is when the lines trip, it weakens the network by electrically. What it means is the reactance between the two sources becomes higher and higher as the line trip, parallel lines trip one after another, and this leads to then angular separation between sending end and receiving end becoming very high, and the system becomes unstable. And this phenomena is also called load encroachment phenomena, which we'll discuss when we discuss the protection aspect tomorrow. Some of the stability measures, high speed fault clearance. You all must be aware that for 400 kV and above, the fault clearance time, electrical fault clearance time is mandated by CA's technical standard to be 100 milliseconds. And for 132 kV, it is 165 milliseconds. This is basically keeping in mind again the stability of the power system, because longer the fault clearance time will result into higher angular separation between the sending end and receiving end, and higher angular separation means when it angular separation becomes more than 90, we saw that it will become system will become unstable. That is also a reason why in Indian power system you have circuit breaker failure protection, so that if the high speed fault clearance doesn't take place because of the stuck breaker condition, still the fault will be isolated within 200 milliseconds by LBBU protection. So you can see how the critical requirement of stability of the power system is made by different protection scheme as well as the control schemes. We talked about single pole tripping and single pole auto reclosing. There are a number of other measures which can be adopted by generating stations as well as the transmission network to maintain stability. Some of the measures are listed here. Shunt compensation, basically this will improve the voltage stability. So you know that now static power compensators and SVCs are being commissioned in Indian 400 kV power system. Steam turbine fast valving is one of the method to reduce the prime mover power when there is a fault. When there is a sudden drop in the active power output on generator side, the fast valving, fast closure of the steam control valves will reduce the mechanical input to the generator. So again, the accelerating torque will become lesser. In some situation, you will have to resort to generator tripping. High speed excitation systems are being mandated. Separation schemes instead of grid collapse, which is a partial grid collapse, would be uncontrolled collapse. Control separation and load shedding scheme are proposed. Special protection schemes are being maintained. So these are various measures which are provided. There are also some of the measures which on the transmission side are basically capital intensive, providing reactive power compensation by way of shunt capacitors. We talk about static power compensators. Then with the shunt reactors to control high voltages, synchronous compensators, static power compensators. So these are some of the measures being implemented to prevent voltage rise. Shunt capacitors are generally used at a lower voltage levels, and static power compensators and SVCs and STATCOMs are being used at a EHV level. This is a simple principle of a static power compensator. There is a fixed capacitor and thyristor control inductor. So together they give the control compensation for reactive power in leading as well as in lagging. In both the sides, power factor reactive injection can be adjusted. Generator based compensation we have already discussed as part of the capability curve in underexcited and overexcited mode. We talked about the synchronous condensers also. In order to maintain the system stability and preventing from the voltage collapse at the system operator level, that means at the National Load Dispatch Center as well as Regional Load Dispatch Center, there are various countermeasures which are possible. There is a use of modern SCADA systems for supervising the angular at various bus bars. Earlier, it was being used by state estimation software. State estimation programs were run periodically to see for the given loading of the transmission network, how much will be the angular separation at between various bus bars. And nowadays, instead of state estimation programs which are run in the load dispatch center, we also have now what is called phasor technology, PMU. So all 400 kV stations, you must be aware that it is mandated now to have phasor measurement units installed, and this phasor data is conveyed to the load dispatch control centers, where they get the complete overview of the system in terms of angular separation and how much is the margin available. And this system basically provides alerts whether when system operates closer to the stability limit in terms of angular separation, it can generate certain control measures, or it will direct some manual actions to be taken for correcting this situation by way of various compensation devices like series compensation, shunt compensation, synchronous condenser, static power component, STATCOMs. These all come under the terminology of FACS devices, flexible AC transmission devices. And these are now required to be widely put in service to control the system and keep it in the safe margin from the point of view of stability. This is the slide which actually gives the same power flow equation and how the series compensation helps. When you do the series compensation, basically what you are doing is you are altering the X. That means you are actually changing the reactance of the transmission line. So by reducing the reactance, you are improving the power flow capability of the line. You know, again the same equation. By parallel compensation, that is shunt compensation, we basically affect the voltage here. In series compensation, you vary the reactance. Parallel compensation, you affect the receiving end voltage, you boost the receiving end voltage, and by load flow control, you actually control the angular separation between sending end and receiving end. This load flow control can be either by the flexible AC device like unified power flow controller. There are devices which are actually controlling the active power as well as the reactive power flow. These are the again thyristor control devices. Also, there is a concept now being used for phase shifting transformer. In the transmission network, you can introduce the phase shifting transformer, thereby altering the power flow in one particular corridor. So these are the some of the compensations which can be given in the transmission network. This is what is explained in these slides. FACS devices. And similar technologies are also used for congestion management. Congestion management is a highly advanced power system where the generation capacity is not matching with the evacuation capacity or transmission corridor capacity. Am I audible? Because I got a network alarm. Can you hear me?
Yes, sir.
Yes, sir.
Yeah, okay.
Yes, here also.
Okay.
Okay.
Yeah. So these FACS devices can also help by providing this compensation is increasing the loading margin. By providing the series compensation or unified power flow devices, actually you can increase the loadability of the transmission line. So transmission can be loaded right up to their thermal capability. So this slide basically I explain what I have already said. These are reactive power control methods. We talked about excitation control from the generating side, use of tap changing transformer, OLTCs, switching in shunt reactors. During low voltage condition, you switch them in. In light load condition, you remove the reactors. Use of series capacitors for long transmission line by compensation. This is a series compensation. OLTC's on-load tap changer at the load side. Static shunt compensation. Again, this is done more on the 132 kV and below. Synchronous condenser. So these are again various measures which are taken on the grid side. Automatic control on the transmission network through load tap changer, on-load OLTC. Now, most of the ICTs in our grid, 400 kV to 220 kV ICTs, they are provided with on-load tap changer. But from operation perspective, at many places, they are not really operated because of the fear of failure. OLTC is considered as one of the weak links in the power transformer, and there are, of course, implications in terms of if you regularly operate on-load tap changer, then operation and maintenance related issues. So to overcome those issues and prevent failures, these auto transformers are rarely really used with on-load tap changing, though the on-load tap changing is provided. There was also a case put up from some quarters that all these ICTs in the interconnected network, OLTC need not be provided. Because in the overall interconnected grid, the effect of on-load tap changer is not very significant in terms of voltage control, so they are not needed. But at the same time, if you have got a situation like grid collapse, or prior to that, if there is a islanding of the grid or system separation takes place, then the voltage control within the area or within the islanded system can be effectively be done through these tap changers. Similarly, in the restoration process, especially those hydropower stations which are used for the black start condition, they require voltages to be controlled. So OLTC is also a useful device during system restoration. Line reclosing we talked about. Under voltage load shedding, though it is used as one of the technique in many countries, in India, under voltage based load shedding is still not very much applied. Though under frequency load shedding is widely used, under voltage load shedding is part of the reactive power management strategy. That means if the just like active power management, when there is a deficit of active power, you shed the load. When there is a deficit in reactive power, under voltage load shedding will help in maintaining the voltages. We talk about synchronizing at the generating station end, but at the same way, there is a out of phase synchronization sometimes during restoration or when you have separation of the part of the elements of the grid and you connect them back. There is a possible of out of phase synchronization. And this out of phase synchronization again can be very harmful for the generator. This is a fault record of a out of phase synchronization by almost 180-degree out of phase. And you can see there is a during synchronizing, there is a heavy voltage dip almost to zero in all the three phases. And you can see very heavy using power fed into the system. at the time of synchronization. These are remote synchronization. Sometimes it happens either due to manual error or there is a synchronizing circuit some problem. So both the possibilities, but this is one of the risk which can jeopardize the stability of the grid as well as stresses the equipment, transformers as well as generators. Overfluxing is again one of the common phenomena which is faced either due to high voltage or high voltage accompanied by low frequency. The flux density in the power transformer as well as in the generator core is proportional to voltage and inversely proportional to the frequency. So V by Hertz, this ratio actually governs the overfluxing. And there are many possibilities where overfluxing can take place. At the generating station, it can happen mainly during the islanded operation or due to failure of the AVR. AVR fails to control the terminal voltage and you may have over-excitation leading to over voltage on the transformer and resulting into overfluxing. In terms of frequency, we had talked about primary control, secondary control, and tertiary control. Some of the provisions of this frequency control are given a little more in detail in these slides. Primary control is basically the initial 30 seconds or so when the governor actions of all the generators, whether it's a hydro generator or it is a thermal generator, basically the governor action is termed as a primary control. In India, the actual response has been, there was a circular from CA to test the primary control, primary response periodically, but I don't think it was very successful. But for primary control to be successful, we need to have sufficient online reserves so that the governor can effectively participate in frequency control. The secondary control is what we talked about earlier. These are the controls like AGC, automatic generation control, etc. They are very recently now implemented. So again, we'll have a little more experience and talk about it going forward. So this is, and there are accordingly supplementary control provided under different contingencies. For example, post islanding control, supplementary control can be the frequency. Tertiary more low legislation, generation load can match. See, so this is a sort of wise, you can say. Primary response is 30 seconds in minutes. Secondary control more than 30 seconds. This is less than 30 seconds. This is more than 30 seconds. So this is between 30 seconds to less than 15. And our control usually takes more than 15 minutes to hour. This is all manual. More details on the basically is important part of it as the interview can be for the frequency. Different modes, full warning mode of operation is saying group setting and this of this setting, and then there is a frequency around which this work. In isochronous governor mode, basically it is a basic speed control which takes over and load control. Usually before synchronizing, the governor is in isochronous mode, or during islanded or isolated grid condition, this control mode is utilized so that frequency can be directly corrected by the speed of the turbine, which basically affects the frequency directly. There are other modes of operation in governor. Power control mode, that means it will not respond to frequency. It will keep generating the given set point power control mode, or it can also be called gate limit control mode, where you manually change the gate limit for desired power generation. These slides you can go through more details on the turbine governor. So when we say 5% droop, what it means basically is 5% is of 50 Hertz is 2.5 Hertz. So for 2.5 Hertz change in frequency, the generator will change power 100% of its rating. That means if it's a 250 megawatt unit, for 2.5 Hertz rise in frequency, generation will be changed from 250 megawatt to 0. And if it is low frequency, 47.5, then the generation will be to 100% full rating up to 50 megawatt. So 5% basically is the band within which full generation will be changed. This is one of the slide just for illustration purpose. The transient frequency response, this is actually the not an Indian case, but when there's a loss of generation, you can see the frequency had dropped, and because of the governor primary response, the droop control actually has improved the frequency to this level. And of course, then other resources can be brought online to bring it back. But basically, this is the illustration of primary response. Again, in a similar setting, you can see here the impact of 1000 megawatt getting lost and the frequency correction accordingly. With primary response and without primary response. We talked about the estimation of load seasonally as well as during the day. Different types of load patterns industrial, agriculture, domestic, commercial. So these are the sort of variations based on which generation scheduling takes place. There are certain figures given in this slide which are old figures, but these are basically illustrative. You can say the power number of various today all the regions are interconnected. The power number is perhaps close to 14,000 megawatt. That means if you lose 14,000 megawatt in Indian grid, the frequency will drop by 1 hertz. But this is an old example just to illustrate the what is called system stiffness in various regions. So this gives a sort of a mix of, and system stiffness depends on the inertia of the system and inertia of the load. So if industrial load is predominant or agricultural load is predominant, or if it is a domestic load which is predominant, depending on that, the inertia will change, load inertia will change, and the response characteristic will also change. So as I said that the frequency response characteristics of the interconnected region now is close to, I think, 14,000 megawatt. Inertia of the power system is one of the important aspect in terms of maintaining the stability, because it is a system inertia, and system inertia depends on how many rotating generators mass is connected to the grid. The moment of inertia which is available helps in reducing the impact of sudden change of frequency due to load variations, etc. One of the effects of renewable generation is reduction is inertia, because solar power stations as well as the wind power stations which are connected to the grid through would mean that is around in in the as a result of the union, and it should not be how to in a support the area caused by the renewable generation. This is giving little more details of the FGMO and RGMO. The automatic under frequency based load shedding schemes. These are the sort of figures, different region, quantum of load which is being getting shared. The load shedding. So these are all reference slides which are available to you to go through. Now, one of the aspects which is to be looked at by grid, try to a very narrow band. Generators face and overfluxing situations during system disturbances, isolated grid condition or islanding condition. There is a international standards to which requires that plus minus 5% in terms of voltage and plus minus 2% in frequency. And there should be capability of the generators to run continuously. So this is a frequency band. So this is becomes one of the guiding criteria for frequency-based schemes to limit the frequencies so that it doesn't come under these. It doesn't go beyond the limits. More critical limits are basically imposed on the steam turbines, which are high frequency turbines, and these turbo generators, especially the LP stage blades, low pressure turbine, they have sensitive to low frequency. Hydro turbines basically do not really have that sort of an issue in terms of low frequency operation. So under frequency trip is not provided in many hydro stations, but the thermal units, they all have trip setting of 47.5, which is the lower limit for most of the generators, and small time delay is provided, which is sufficient for primary response from the governor to improve the frequency. Because if you, I remember the good old days, maybe before 2000, thermal units used to trip instantaneously if the frequency touches 47.5. And the moment frequency touches 47.5, thermal units will go up bar and the grid used to have complete collapse. But subsequently now there is a small time delay of say 200 milliseconds or so given. And chance is given to primary response of the generators to improve the frequency subsequent to fall in frequency, and that is held by dA by dt, rate of change of frequency detection relays. Now, one of the measures to incentivize the voltage control as well as the frequency control in the power system, as we said, it needs to be incentivized. Now, the incentives are provided basically as part of the concept of ancillary services. So the ancillary services has been introduced now in Indian market. There are three types of ancillary services. This is the frequency support ancillary service, voltage and reactive power support service, and third is the black start support as a service. So these are becoming now the additional source of revenue for the generating stations who have capability to provide frequency support or active reactive power support, both for controlling over voltages as well as for under voltages, as well as for the black start support during the shutdown. So this has been now rolled out in the Indian power system, and hopefully the commercial incentives will help in bringing down the voltages, just like frequency has been now made very narrow in the operate in a very narrow band. Even the voltage control, as supported by various generating stations.
Sir, ये ancillary service क्या है सर?
Ancillary services is the additional services specifically to support the grid in terms of frequency stability as well as the voltage stability. And these ancillary services basically give financial compensation to people who come forward for such services. For example, if the hydropower station is providing a black start service, it is identified as a sort of a black start station, then they will be compensated financially also to provide that black start service as and when it is needed. So there is a financial incentive to provide for this scheme. We talked about hydro station. Why can't they support reactive power absorption when the voltage is high? And then we said there is hardly an incentive to risk the operation in under excited region. So these ancillary services will help doing that. Even in the renewable generation, for example, all the wind power generation, they have converters between the generation and grid. So they are connected to grid through the converter. These converters can also be used as a static war compensators.
Sir, excuse
Yeah.
me, sir.
Yes.
सर मैं जो क्वेश्चन सर कर रहा हूँ इसमें मैंने देखा जो पहले जो एबीटी टैरिफ था ना,
हाँ,
उसमें यूआई को कंसीडर कर रहे थे. अभी क्या है कि कुछ 3 पार्ट में कॉस्ट कर दिया है. उसमें मैंने देखा एक पार्ट एंसिस्ट्रली सर्विस भी है.
एंसिलरी सर्विसेज. हाँ,
ये जो यूटिलिटी जनरेशन में जो मतलब कॉस्ट हो रहा मिलेनियम यूनिट का,
हाँ,
उसमें मैं देखा हूं कि सर 3 पार्ट में डिवाइड कर दिया. 2 पार्ट तो एक फिक्स चार्ज है और एक एंसिस्ट्रली सर्विस है. तो इसमें से हमको सर डाउट था पहले से कि क्या है ये, थोड़ा सा आसान भाषा में बताइए सर.
बेसिकली ये जो यूआई मैकेनिज्म, कमर्शियल मैकेनिज्म जो था, which help in stabilizing the frequency to some extent. Now, in place of that, now this will be another commercial mechanism which is helpful for frequency control as well as for voltage support to maintain the grid stability. And so you can say ABT regime will be replaced by this ancillary services regime, wherein generating stations will be compensated for frequency support as well as reactive power support, and also for black start facility. Earlier also there was some sort of a I would say commercially some negative aspects were there which were not really helping the reliability point of view to the grid. For example, if there is a high frequency operation which was there in the Indian grid in up to say even 2000 or beyond that, 2005, 2006, nighttime frequency used to be high, but no one will back down the generation. All thermal units to maintain their schedule and to have this good load factor, because there were incentives on load factor and this thing, whereas they were not getting compensated if you reduce the generation to maintain the grid in this. So some of these anomalies will get corrected through these ancillary services. There will be incentive to participate in the frequency control and voltage control. So this is an improvement over ABT regime.
Hello. Hello. Hello, sir. Sir, you are hearing me?
Yeah, I am able to.
Hello.
हाँ बोलिए बोलिए आपकी आवाज
Yeah.
Sir, you are listening me, sir?
Yes,
खटकी
sir,
साहब
can
आपकी
you hear me? I am not.
आपकी आवाज कट रही है सर, पटकी सर.
Again, I try to. Can you hear me now?
Yes, yes.
Yes, sir.
Sir. Hello.
Yeah, go on, go on.
हाँ सर, ये जो अनस्टिट्यूल इंटरचेंज यूआई रेट जो पहले होता था कि फ्रीक्वेंसी डाउन होने से हम जनरेशन ज्यादा बढ़ा लेते थे, तो उस केस में हमारा जो है मतलब रेट पहले फिक्स था। अभी क्या है कि सर हमको रेस्ट्रिक्शन कर दिया कि हम अगर फ्रीक्वेंसी देख के रिटार्डेशन करेंगे तो एक परसेंटेज के बाद मीन्स कि 2% नीचे और 2% ऊपर से ज्यादा हम करेंगे तो हमको डबल पेनल्टी लगता है। तो सर इसके ऊपर कुछ अगर थोड़ा बताएंगे तो हमें अभी तक इस चीज फंडा का क्लियर नहीं हुआ सर, क्या है ये?
आपका पेटकी साहब नेटवर्क चलता चला गया, लगता आवाज नहीं जा रही है आपके पास।
Hello, can you hear me now?
Yes, sir.
Yeah. No, I
Slide नहीं
could
दिख रहा
not
है
hear
लिखा।
the previous. I could not hear the previous question properly. So maybe we can repeat the question.
क्वेश्चन को रिपीट करेंगे जरा, किसने किया था क्वेश्चन अपना?
Or we can go to another question, somebody else.
Any questions from participant sides?
जो पहले क्वेश्चन कर रहे थे उस क्वेश्चन को रिपीट कर दीजिए, किसने किया था? कोई और क्वेश्चन है? दूसरे आदमी क्वेश्चन कर सकते हैं। तो ये कोई बोल नहीं रहा कुछ भी, सबके म्यूट है। किसी पार्टिसिपेंट से कोई क्वेश्चन है कि नहीं? काइंडली क्वेश्चन कीजिए, जिन्होंने पहले किया था वो रिपीट कर सकते हैं या नया क्वेश्चन पूछिए कोई। आवाज नहीं आ रही किसी को क्या? एनीबॉडी रेस्पॉन्स कोई तो कीजिए कि आ रही है आवाज कि नहीं आ रही।
हाँ आवाज आ रही है सर।
आवाज आ रही है।
यस सर, आवाज आ रही है सर आपकी।
तो यस कोई तो कोई बोले ना, यस कोई बोल ही नहीं रहा था। यदि किसी का क्वेश्चन है तो क्वेश्चन कीजिए ना फिर, या जिन्होंने पहले किया था वो रिपीट करें क्वेश्चन को। नेटवर्क के कारण, नेटवर्क की प्रॉब्लम के कारण पटकी साहब को सुना नहीं है क्वेश्चन वो।
मैं बोल रहा हूँ सर, मैं क्वेश्चन किया था कि
हाँ,
जो
क्या नाम आपका? आपका क्या नाम है?
अरुणाभा मुखर्जी।
हाँ तो हाँ मुखर्जी जी, आप फिर से क्वेश्चन को रिपीट करिएगा।
हाँ सर,
क्वेश्चन अपना रिपीट कर दीजिए, पटकी साहब ने
हाँ
सुना
मैं
नहीं।
बोला था कि अनशेड्यूल इंटरचेंज जो है यूआई में पहले ये रूल था कि हम अगर बैकडाउन फ्रीक्वेंसी देख के जनरेशन बढ़ाते थे और फ्रीक्वेंसी देख के जनरेशन कम करता था, तो अकॉर्डिंगली हमारा रेट फिक्स था, हमारा जो है पैसा उस हिसाब से मिलता था। अभी क्या है कि ये जो एनसीएसटी टैरिफ आया है कोई एबीटी के बदले में, जो 3 पार्ट में डिवाइड है, एक रनिंग कॉस्ट, एक फिक्स कॉस्ट और एक एंसेस्ट्रली कॉस्ट। तो वही एंसेस्ट्री कॉस्ट क्या है वही समझ में नहीं आ रहा था। सर को इस वजह से पूछा कि एंसेस्ट्री कॉस्ट क्या है, तो सर ने तो बहुत कुछ बता रहा है, तो मतलब मेन पॉइंट को सर बता देंगे तो हमें एकदम से समझ में आ जाएगा, और थोड़ा फोकस करके बताएंगे तो सर समझ में नहीं आया।
ओके ओके, पटकी साहब क्लियर हो गया आपको क्वेश्चन?
हाँ, basically ancillary services, you have to declare what sort of services you can provide. I gave one example, like your station can provide, for example, the Black Start service, or you can say we can provide the voltage support services during this time. So like that, just like you are scheduling for active power generation, similarly, you can now schedule for these ancillary services for voltage support, frequency support, and backstart support, and you will be then compensated for providing that service. That is the additional part compared to the earlier regime.
Okay, sir. Okay. Thank you, sir.
Any other question? Any clarification?
सर
Any
आप लोगों ने
doubt?
जो क्वेश्चन दिया था सर, ये जो हाई स्पीड ऑटो रिक्लोजिंग, मतलब हाई स्पीड, लो स्पीड, मीडियम स्पीड ऑटो रिक्लोजिंग भी होता है क्या? ना सिर्फ हाई स्पीड ऑटो रिक्लोजिंग ही होता है?
दोनों होता है, हाई स्पीड एंड लो स्पीड ऑटो रिक्लोजिंग बोथ आर पॉसिबल। दोनों का पर्पस अलग अलग है। इन high speed auto recloser basically helps in transient stability, as I explained today, whereas the medium speed or high speed auto reclosing is more for restoration purpose subsequent to tripping. It allows sufficient time for fault to completely get deionized, as well as safe to switch in with from remote end, and then you close at generation station end. So more time is allowed. So the purpose is more to ensure that fault is fully cleared, and also it is a auto restoration. Whereas the high speed reclosing is mainly for maintaining the stability. That's the difference.
The ideal time of high speed, sir?
Ideal time of high speed reclosing is the आपका जो at present the high speed auto recloser is immediately after the main protection has operated and breaker is open by the main protection. The reclosing cycle starts, and your dead time, which is 1 second delay, is the to complete the reclosing cycle. So this is at present adopted setting for auto reclosing. This dead time is basically again to ensure that fault is completely isolated and it is safe to re-energize so that auto recloser becomes successful. So 1 second dead time is adopted. In future, going forward with the modern mechanisms, it's possible to reduce the dead time. And there are systems in the world where dead times is 600 or 700 milliseconds also. It requires measure like um, in order to reduce the secondary arc phenomena, etc. Measures like neutral reactors in the transmission lines and wherever reactors are provided. And there are also possibilities of multi-phase auto-reclosing also. Multi-phase auto-recloser also prevents secondary arc phenomena due to induction from the neighboring line. So there are possibilities, but in India, dead time is 1 second, and it is only single phase. It is not multi-phase auto-reclosing as well.
So auto reclosing, what we have seen in every power station, is basically the old power stations depends on the PLCC's carrier communications. So is there any latest technology that it is sure shot the auto reclosing will happen carrier communication without PLCC or any other latest technologies?
Yes, in the latest scheme, actually, you don't need auto reclosing with communication aid, because it basically goes by the principle of voltage detection at the sending end only, where auto reclosure is being executed. So dependence on status of the remote end breaker or remote end voltage level, etc., is not required for the scheme at the end where you are doing the auto reclose sequence. So communication is not really needed nowadays.
Okay, sir. Okay.
Hello.
Yeah.
Hello. Hello, sir. Sir, I am from Chamera 2 Power Station. My name is Ravi Kumar. Sir, I have questions regarding AGC. Sir, our power station, we have operated machine in under AGC. Problem that we have faced are two. First of all, that due to AGC, our daily targets of generation were not met. Secondly, due to variation in such an just suppose we have machine of 100 megawatt, and the set point given by the authority is from 25 megawatt to 100 megawatt. Under 5 minutes, our machine, which was running on 100 megawatt, comes to 25 megawatt, and then after 5 minutes, due to change in frequency, it reaches to 100 megawatt again. It causes problems in machines also. And is there a way, suppose that this gap between demand and generation could be met? Yeah, is there any percentage of deviation from scheduled energy? Is there any सवाल ये है कि सर जैसे हमारा शेड्यूल्ड है, मान लीजिए 100 मेगावाट का है मशीन का, और एजीसी ने हमको 25 मेगावाट दे दिया, हमारी मशीन 25 मेगावाट पे चली गई, और फ्रीक्वेंसी तो इंस्टेंटेनियसली चेंज होती रहती है। उस फ्रीक्वेंसी के चेंज होने पे फिर वो वापस से 5-10 मिनट में तुरंत 100 मेगावाट वापस चला जाता है। तो इससे हमारे मशीन को एक तो इतना वेरिएशन लोड का हो रहा था उसमें मशीन में, पहला तो प्रॉब्लम ये हो रहा था। दूसरा कि अगर जैसे किसी एरिया में सब मतलब कितना परसेंटेज ऑफ चेंज एक पावर स्टेशन के लिए अलाउड है एजीसी में, कि हमारी 100 मेगावाट की है तो हमको 90 मेगावाट या फ्रीक्वेंसी के हाई के रिस्पेक्ट इतना हाई जाएगा तो इतना डेविएशन मैक्सिमम होगा हमारी तरफ से, क्योंकि एक पर्टिकुलर पावर एक यूनिट को इतना वेरिएशन करना विद इन दिस मतलब इतना कम टाइम में उसके लिए यूनिट के लिए ठीक नहीं है सर, उसका ऑपरेशन में प्रॉब्लम आता है काफी।
Yes. I agree with you. I don't exactly know how the AGC has been implemented, because it's a very recent thing. So details, I'm not aware of the details, but generally when AGC is limited, it doesn't, there has to be a sort of hysteresis allowed, within which there won't be any action by the HGC controller, as well as there will be a sort of a dead band, so that very frequently changes will not be allowed. As you have seen, the primary response and is not really a instantaneous response. AGC is a secondary response. And you see the time horizon of the secondary response which is expected, it is in seconds and minutes. So AGC is not expected to respond to the instantaneous changes. So perhaps you can point out to the people who are responsible for the scheme. I don't have the right information in terms of implementation right now, but certainly it should not be responding to instantaneous changes.
Okay, sir. Okay, okay. Yes, sir. Okay. Thank you, sir. I got it.
Any other clarification? Or
Sir, this is
otherwise,
Atul Pandey from
Sir.
Chamera 3 Power Station.
बोलिए, बोलिए.
Sir, I want to know that when any hydro generator is running under condenser mode, so means to implement that condensing mode in the machine, what design aspects we should consider, or which means the U curve, V curve, which variations take place in U curve, V curve, or we can say capability curve, or whenever running means our machine, if our machine is running in condenser mode, exactly at what point of capability curve our machine is running. If you can show me by showing that slide again of capability curve, at what exact point condensing mode is occurring in our machine.
Basically, when we talk about condenser mode operation, it is on the capability curve on the vertical axis, that is a reactive power axis. Operating point will remain with a megawatt almost close to zero, except whatever stray losses which are occurring as active power loss. It will be basically on the vertical line of the capability curve, on the MVR line, on the overexcited region as well as underexcited region. So on the capability curve, both these upper limits and lower limit in the underexcited and overexcited mode, that has been given. As far as the modifications on electrical side, capability wise, there are no modification, except that for the governor control and the excitation control, there has to be a condenser mode selection, so that appropriately the other controllers should not react. So the condenser mode in both these controllers will have to be adopted. And as far as turbine is concerned, in the condenser mode, because it will be just turning in the, I think, without main inlet valve remaining open. So on turbine side, some modifications will be needed to ensure the hydraulic side remains stable in the condenser mode without causing any overheating to the blades. In some of the condenser mode operation, also there is a cooling facility. So water jets are put so that turbine blades are cooled continuously with the water, and there is a dewatering system. So main modifications are more on the turbine side rather than electrical side.
Sir, exactly, can you show me again that capability curve, Anna? Actually, I want to see that exact point at which our machine will be running in condenser mode.
Okay, 1 minute.
सर प्लीज अभी हुआ का क्यों चल रहा है क्वेश्चन आंसर
Are you able to see the capability curve? Can you see?
Yes, sir. It's visible. I can see.
So on this capability curve, this is the 0 megawatt point, this one in horizontal axis. And this is your reactive capability. So at 0 MW, basically during condenser mode, you will be basically operating in this region on vertical axis, in the reactive power axis. So this is the region where you are operating. So capability curve wise, there is no modification. As I said, only you need to select that mode, condenser mode, so that the other parameters do not play any role. And in governor mode also, condenser mode will have to be given. And there may be some protection settings which will need to be changed on generator protection during condenser mode of operation. Like if you have got a reverse power protection or some other protection, so that they don't maloperate during this mode. Governor mode also, because you will be synchronized with the grid and the MW power will be 0. So again, the governor mode will have to have a condenser mode selection so that it will permit you to close the breaker with 0 MW. Otherwise, it will try to open the main inlet wall to pick up load immediately. So some governor modification and AVR modification in terms of controllers, but the major modification will come in the turbine side, where you may need to have dewatering system and maybe some cooling jets will be required in the, depends on the type of turbine and the manufacturer's recommendation.
Okay, sir.
Is it clear now?
Yeah, it is clear. So electrically, we don't need any design modification for condensing mode, right?
Except on the some control circuit modification in governor and
Yeah,
AVR.
that is okay. Yeah. Okay, sir. Thank you, sir.
Sir.
Yeah.
So you said that most preferred for reactive power compensation, static compensators are used. That's it.
Yeah. At EHV level, static compensation.
Then what about the harmonics introduced by this static equipments?
Yes. Normally, these static equipment go along with some filter circuits. So some filters are needed to control the harmonics.
Okay.
If there are no any clarification, can we close it now?
Yeah, we can close tomorrow while starting. If any more questions are there, we'll start with the questions on day 1 before we start the program of day 2 tomorrow. So
yes,
we can think of some questions.
A participant can study today, and any question, if any clarification, they can ask tomorrow.
Yes, we can close for the day.
So we are closing for today's session. Thank you very much, Patki Saab, and so nice of you that both the sessions were conducted very nicely, and it was very good participation was also there. Number of questions asked by the participants. That's very nice. and we hope that tomorrow's program will also be very good. For the information of participants, that all these slides we will sending to the corporate office, and they will share it with the consent participants, or otherwise, if possible, we can give it on the group also, and you can study that slides and ask any question clarification from Patki sir. Thank you very much for today's program. Thanks a lot, all the participants. Thanks a lot to Patki sir. Thank you, sir.
Thank you very much.
Thank you, sir.
And tomorrow
Thank you, sir.
we will start at 10:30, and because there is no inauguration session tomorrow, so we will first session will be 10:30 to for 90 minutes, and after that some questions we will take up, and second session as usual at 2:30. First session we will start at 10:30 sharp. Kindly connect yourself at 10:25. Thank you.
Thank you. Good night.
Okay, good night.
Okay, sir. Thank you, sir.